Okay, so hopefully you all got a big scary warning. And Matt, do you want to test that everything will share and so on correctly?
Sure. Yeah. What the heck?
I can hear you. So
that's step one. Let's see. Okay. Good thing I tried. I have to just looks like I have to restart Zoom. So I'll be back.
okay, sounds good. We'll be here. Okay. You're back?
Yes. Permission granted to Zoom to share my desktop.
Yeah, that one. Okay, so I can see your slides. Looks good.
Great. All right. Success.
All right, perfect.
2 minutes to spare.
Yeah, and I can see that people are filing in too. So I think I've done all the juggling of YouTube links and so on. So we'll wait till the right time to start. Yeah, Matt, I don't know if you noticed, but your book was name checked in a previous talk. We used benchmarks.
Furby, yeah.
Yeah.
That's awesome.
Yeah, it's good because it's well, we were looking for code that is where the impact of accuracy, where there's some clear sense of like why would you want lower accuracy to go faster, and so PBRT seems like a good example of that.
Yeah,
but we'll find out more about how much that assumption is warranted in a moment.
Well, there is actually a feedback loop here because actually I rejiggered some of my slides in light of that because that kind of brought me in some new directions. So so I do have more to say about that, but it has been partially influenced by this morning's presentations.
Oh, that's great. Yeah. Okay. I think that's exactly what we want out of FPTalks. So. Okay, so as folks are kind of coming back into the Zoom, so we'll be starting in just a moment. Kind of same structure as in the first couple sections in the morning. So the questions will be on Slack, and I've already started the thread for Matt Pharr's talk. And again, Zach will be sort of emceeing the questions so that I can do the various website updates and Slack jiggering as well. So I hope you're all excited for the next two sections and maybe grab something to eat in the meanwhile. You know, if that lined up with the lunch break for you. Okay, so I think we should get started. It's 2 p.m. Pacific by my watch. So our next talk is from Matt Pharr. Matt Pharr is a distinguished research scientist at NVIDIA Research, and he works on real-time rendering algorithms. And actually so one of the things he's well known for is this book, Physically Based Rendering from Theory to Implementation. It's widely used in university courses. I hear also in industry. It's kind of a standard textbook in graphics. And it was even name checked in one of the earlier talks as a source of benchmarks and interesting computations. So here's Matt telling us about accuracy for rendering. Please go ahead.
Alrighty, cool, thanks. Yeah, it was amusing this morning to hear, I think it was Mark Dickinson who said that he thought he was here today in part because of Stack Overflow interactions about Herbie, and I think I'm here today because of bugs I filed against Herbie when I was using it a few years ago. So here we are. Okay, great. So yeah, let's talk a little bit more about rendering. So just as context, Theo gave a great talk this morning about kind of the hardware side of floating point and kind of all the craziness that's possible there. And that was super interesting. And I hope, my topics will be more focused on like the software and algorithms perspective. And I'm just going to assume that the hardware is fixed and kind of IEEE float and kind of a normal stuff over there. So I should also add that everything I'll be saying in this talk is my opinion and not necessarily NVIDIA's official viewpoint on any of this stuff. Okay, so I think it's probably widely known that that rendering is a fairly intensive floating point computation. There are millions and millions of GPUs being built to do it, and people buy them and use them. And rendering is widely used in entertainment and product design and architecture and so forth. But it's very floating point intensive. So here's a rendered image of a pretty nice scene. And this took 60 seconds on a modern top of the line GPU. I think this kind of passes, at least to me, it kind of passes the Turing test for it looks like a photograph. We're kind of getting to the point where you can start to fool the humans with what computers can do. But if you add up the work, this took about, if you look at the peak performance of this GPU and add it up for 60 seconds, it's about 2 petaflops of computation. Of course, some of those floating point units were idle and so on and so forth, but, quite a bit of computation went into these pixels and, most of it floating point. So if you kind of zoom in, this is a zoom in of a coffee cup on the table. And, if you zoom in even further and, you start to look at the individual pixels of that coffee cup, and you divide out your total computation by the number of pixels, you can find that, you're looking at about 760 megaflops, for every pixel value. And that's kind of funny, right? Because, the output is in this case, 3 FP16s. So there's an enormous amount of work going into those 48 bits coming out at the end at every pixel. So first question might be, well, why? What's with this kind of huge, mismatch, between these two things? And I think the best way to explain it is that kind of modern rendering has kind of turned into a physical simulation problem. and rendering algorithms are really about kind of taking a ray optics model of light, applying Monte Carlo integration to kind of randomly sample light paths, and then just kind of simulating light in a scene, and implementing some simulation of film sensors and lens systems and how surfaces scatter light, and you kind of put all this together into a simulation. You can make an image, but it takes a lot of flops. But schematically, you're just kind of following these paths of light. How much light is there under the chair? Well, if I bounce light around from the outdoors, I can kind of start to estimate that. And if I do that every pixel, I get an image. And because it's based on Monte Carlo, you're just following these random paths, and you follow lots of paths per pixel. So if you only follow a single light path per pixel, you get this kind of systemic noise, this kind of graininess. One might even more ask, kind of why do we care about accuracy? We're running lots and lots of trials, we're averaging them together. If one of them goes wrong, what's the problem with that? There are a couple answers to that, but I'd like to talk about another constraint with rendering, with the rendering problem before we go further, which is that pretty much all of it is in this context of a fixed computation budget. And if you're doing real-time graphics, you've got a 30th of a second, and every 30th of a second you have to make an image, and then you start from scratch and make a new image. And if you're rendering a movie or something, you have to finish it by the release date, or maybe a couple of weeks before. But in any case, you have some amount of computational resources you'd like to apply to making pictures, but the amount of the cycles you have are limited in one way or another. And at the end of the day, that's what limits the simulation accuracy, and that's what limits the complexity of the scenes we can render. Is kind of fixed computation or limited computation. And there's this kind of virtuous cycle that comes out of that, though, which is that if you can improve your algorithms, if you make your algorithms run faster, then you have excess computation budget. Then you have computation you haven't used. And so what you can do is you can improve the quality of your simulation. You can improve the complexity of the scenes you're rendering, and you get better images. So there's this direct connection between kind of efficiency and performance, and then the quality of what comes out in the end. If someone's making a game, if they have a 33 millisecond frame time, if it's optimized and now it's running in 20 milliseconds per frame, no one's going to say, great, let's just let the GPU be idle for 13 milliseconds. Everyone's going to say, great, what more can we do with 13 more milliseconds? So you get a richer image in the end. This gets to my kind of first thought, and I was saying to Pavel at the start of the, before we started, that kind of this morning's talks kind of made me respin this middle part of the talk here, which is that I really think that, there's a lot of opportunity for improved performance through approximation, and both Furby and the talk on, I can't remember the name of the title, but the system was Daisy. I think, there's great opportunity for benefit here, to rendering. I kind of like this idea, that kind of, traditional compiler optimizations, have kind of hit, we've kind of hit their limit, and, you're getting 1% or 2% a year, but traditional compiler optimizations really aren't delivering performance. There's maybe an analogy here to kind of post-Moore's law hardware, right? We're kind of, that, a lot of that has been tapped, and now where do you find the next, where do you continue to find performance? It's not going to be through better common sub-expression, evaluation. So I think there's a lot of opportunity here, especially in rendering, where we have this massive ratio between, hundreds of millions of flops, per pixel, per single RGB value coming out. There are many challenges in this. There's a long path between, research tools and actually, things programmers can use. It's you'd like it to be as easy as -F fast math. You'd like to be just as fast as -F fast math. Obviously it's much more complex, so that's probably unattainable. But I think to the extent to which graphics is so performance driven, that getting tools in programmers' hands could actually be quite meaningful. If they can kind of truly scale to kind of production complexity, and so on. So I think that's really exciting. Second thing I'd like to mention briefly is geometric error in ray tracing. And this is kind of a, this has kind of been a long-standing challenge with rendering algorithms, where kind of numeric error, the connection, this is where we kind of most often see numeric error leading to error in images. So what I mean by that. So, all of this light transport simulation is based on the ray tracing algorithm, where basically, you're kind of saying from this point in the scene, in this direction, what object do I see? What's the first thing a ray intersects? You compute that using floating point math. And you know how that goes. So you may well compute that intersection point, as here as being inside the sphere when it should be on the surface of the sphere. And then the problem is, if you want to continue your light path and say, well, can I see my light source? Well, you can't. You intersect the sphere, you say, oh, I guess I couldn't see the sphere from that point. Whereas in point of fact, if you had computed at an accurate intersection point, the true intersection point, you would have found out that kind of I am getting light from the light source. So here's an example of that error in practice, and it's really kind of pernicious because the entire image is actually darker than it should be. You can very obviously see the error in that. So the correct image is on the left, the wrong image is on the right. On the right, you can see that stripe, where basically sometimes, but not always, these intersection points are below the surface and they're not making it to the light, even though they should. But the whole image is actually a bit darker than it should be, just because we're having this kind of inaccurate geometric computation. And this is very different than like computational geometry. There's all sorts of work in computational geometry on like robust predicates and techniques where you fall back to more and more precision until you're sure you have the right answer. But we'd really like to not pay that cost in graphics. It's not worth that cost. So really, we're in this situation where what we'd like to do is kind of, at least consistently have the lesser error. Make sure that computed point is on the right side of the surface, not on the wrong side of the surface. So, in some ways, that's a much easier problem. There's been a bunch of work on this area. Of course, you can apply higher precision and people apply interval arithmetic. There's no end of hacks and kind of fixed epsilons, which sometimes work until they don't. I think as is the case with all epsilons. I've done some work on just kind of the straightforward working through the forward error bounds for kind of these algorithms, and then using that to kind of derive robust points on the correct side of the surface. This is written up in the book. I would actually be happy to get feedback on this from people in the floating point community. Hopefully it's not too embarrassing, but I think the section kind of lays out the problems and at least a first stab at a solution to it. Okay, with that, I'm already over my time, so I'll stop there and say thank you.
Many thanks. This is super interesting, and I love the sort of. I don't think I'd quite heard somebody phrase it this way. Like, what are the right tools for a post-Moore laws, post-Dennard scaling world? I think that's a great vision. And as Theo was saying earlier, it seems like there is plenty left to exploit. I think one thing that sometimes becomes challenging for a lot of maybe the research side of the floating point community is getting access to the right benchmarks and something that's sort of small enough to make progress on, but big enough to be interesting to practitioners. Mm-hmm. So is there, so like that scene was sort of a full minute on really high-end hardware. Well, a lot of times researchers don't necessarily have the highest end hardware or necessarily those code bases. Do you have any advice for how, we can get the challenge problems to start moving tools in that direction?
Yeah, I mean, that kind of walks into a massive self-plug, but I'll start with that. Right, so this book that Pavel mentioned at the start, Physically Based Rendering, is, it's a literate program, Donald Knuth style, kind of, explaining how to write a modern physically based renderer. It has accompanying source code, of this system. And actually that is what I used for rendering all the images in this talk. And we try to provide a variety of kind of decent, scenes to render and kind of content for people to use with the system. It's fairly widely used in graphics research. People will, grad students will implement algorithms in it and then use this to publish their papers. And, it's kind of sophisticated enough to be plausible without being like the full complexity of a production system. It's maybe 70,000 lines of code.
Yeah, I know that we already have some PBRT in FEbench thanks to Brett and the Furby work, but I think this is just more incentive to keep adding it. We did have another question here in the chat. I think kind of related to this domain knowledge that lets you know if you do have error, one side is better than the other. So Chandra, I don't know if you wanted to ask about this aspect where like asymmetry in the error helps, and the domain knowledge that goes into that.
Yeah, no, that's a really good question. And actually it's a little bit more complicated because, like if the surface is transmissive, if it's translucent, then actually you want to be on the other, and your light path is continuing, sometimes you want the light path to continue on the other side of the surface, reliably. So then there's even more context about like, what's the right side to be on. Yeah, so it's a good question. I don't know. It's hard. I don't have a good answer to it.
That's great. I do want to keep us roughly on schedule, or Pavel will yell at me in our private channel. So I think I'm going to switch back to him. But thanks so much for being here. It's a great talk. I love that vision. And as always, folks, if you have additional questions or thoughts, please pipe up in the Slack. But I think with that, we'll hand it back to Pavel.
Cool. Yeah. Thanks for having me. And I'll be on Slack.
Yeah, absolutely. There's a lot of questions in the thread already, and I think there will be many more. So our next talk is from Jay Lim. So Jay's he's currently a PhD student at Rutgers University, but not for long. He will soon be starting a new job at Yale University as an instructor. And in his sort of most recent research, he's been interested in like the fundamental principles behind generating correct low-level numerical software. So that's what he'll be talking about today. Jay, please take it away.
Awesome, thank you. Can you guys hear me? Perfect.
Yep.
So hello, again, my name is Jay Lim, and I'm a PhD student at Rutgers University with my advisor Santosh Nagarkate. Today, I would like to share an exciting method for approximating elementary functions for 32-bit representations. Oops. Oh, there we go. So all endeavors in science, from structural engineering to scientific simulation, and they use math libraries to approximate elementary functions like e to the power of x, sine of x, and so on. But unfortunately, mainstream math libraries produce wrong results, which can possibly lead to catastrophic consequences. So the goal of our work is to create approximations of elementary functions for 32-bit representations that produces correctly rounded results for all inputs. In the context of the RLibM project, we have been making a case for approximating the correctly rounded result of f of x instead of trying to approximate the real value of f of x. And if you do that, you can use linear programming problem to generate these polynomials. Now, to make this idea applicable for 32-bit representation, in this presentation, we make 3 contributions. So first, instead of trying to generate a single polynomial, we generate a piecewise polynomial. Second, we use counterexample guided polynomial generation that is inspired from program synthesis to handle millions of inputs from 32-bit representations. And third, we propose numerous methodologies that supports variety of range reduction. And our resulting elementary function not only produces correctly rounded results for all inputs, but is faster than mainstream math libraries that have been optimized for decades. So now let me first start off by telling you what correctly rounded result even means. So consider this real number line here. 32-bit float can only represent finitely many values. So if you can't exactly represent natural log of x1 in this blue circle here, then you have to round it to a float value. In our case, is going to be the green v1 value. So the v1 is the correctly rounded result of natural log of x1. And an approximation function that produces correctly rounded results for all inputs is called a correctly rounded approximation function. Now, the most commonly used method for approximating an elementary function is with a polynomial. And all mainstream math libraries have been generating this polynomial using the minimax approach, which tries to approximate the real value of f of x. Now, this might sound okay if you're in the context of real numbers, but in finite precision representation, this creates a number of challenges because Minimax approach only allows a small amount of error to produce a correctly rounded result. And otherwise, you will produce a value that will round to an incorrect result. So in the RLibM project, we have been, instead of trying to approximate the real value of f of x, we have been making a case for approximating the correctly rounded results, the v1 value. And the intuition is that there is a range of values around v1, right? Where sorry, let me step back really quickly. So the intuition of why we should approximate the correctly rounded result is that there is a range of values around the correctly rounded result, v1, where if you produce any value within this interval, the final result will round to the correctly rounded result. And we call this the rounding interval. And by approximating the correctly rounded result, as you can see from this larger gray box, we provide more freedom in generating polynomials that produces a correctly rounded result. So RLibM has been generating polynomials by first computing the correctly rounded result of f of x, and then for each of this result, identifying this rounding interval. These rounding intervals actually constraints are linear constraints on the polynomial they want to generate. So we encode these linear constraints into linear programming problem and use a linear programming solver to generate the polynomial. Now our question is, how can we make this work for 32-bit representations where there are 4 billion inputs? To make the RLibM idea applicable for 32-bit representations, we make 3 contributions. First, trying to generate a single polynomial that produces the correctly rounded results for all 4 billion inputs might require really, really high degree polynomial, which is not great for performance. So instead, we propose to create piecewise polynomials by splitting the input domain into multiple subdomains and then generating a polynomial for each subdomain. Now, to efficiently identify which polynomial to evaluate given an input, we split the domain based on the bit pattern of the input so that we can just mask a few bits and say, hey, this input belongs to subdomain number 2. Use that polynomial. Now, second, even after you split the entire input domain into smaller subdomains, we might still have millions of constraints, and LP solvers cannot feasibly handle millions of constraints. So we use a counterexample guided polynomial generation, which is inspired from program synthesis, by first sampling a few inputs from the subdomain. And using just these inputs, we generate a polynomial that satisfies the inputs in the sampleable. Now we take this polynomial and check whether this satisfies every single rounding interval constraint in the subdomain. And if it doesn't, we add these inputs to the sample again, and then use these inputs to generate another polynomial, and repeat this process until the polynomial we generate produces the correctly satisfies the rounding interval constraint for in all the rounding interval constraints in the subdomain. Third, we propose methodologies that supports various range reductions, but due to the time constraints, if you want to learn about these techniques, please refer to our PLDI 2021 paper. Now, using these techniques, we created RLibM 32, which contains several elementary functions for 32-bit float and 32-bit posit. We used the MPFR math library with at least 200 precision bits to compute the correctly rounded results for these representations. And we evaluated all of our experiments on a machine with 2.1 gigahertz Intel CPU running Ubuntu 18.04. Now, in our experiments, we were interested in 2 questions. Does RLibM 32 actually produce correctly rounded results for all inputs? And if so, how fast is RLibM 32? So to compare the performance, to measure the performance, we compared RLibM 32 against Intel and glibc's math library, which are the 2 most commonly used math libraries, and also against CRLibM, which is a correctly rounded double math library. Again, in this presentation, we only show our evaluation results with our float functions because of the time constraint. If you're interested in seeing our entire evaluation, please refer to our paper. Our experiment shows that RLibM 32 does indeed produce correctly rounded results for all inputs. In comparison, glibc's float and double math library and Intel's float and double math library does not produce correct float results for all inputs. Even using crlibm, which is a correctly rounded double math library, doesn't produce correct float results for some of the inputs because of the double rounding error. Our experiment also shows that rlibm32 is fast. So in this graph, we show the speed up of our float functions against glibc's float and double math library, and a speed up of 1.0 means that rlibm32 is faster. On average, rlibm32 has 1.1x speed up over glibc's float math library and 1.2x speed up over glibc's double math library. Now, compared to Intel, rlibm32 has 1.5x speed up over Intel's float math library and 1.6x speed up over Intel's double math library. In our experiments, we found out that Intel math libraries, even though it doesn't produce correctly rounded results for all inputs, it produces more accurate results compared to the glibc math library. And because of that, rlibm32 has more speed up over Intel compared to glibc. Now, rlibm32 has 2x speed up over crlibm, and this is because crlibm is a correctly rounded math library for the double representation. So crlibm naturally produces the most accurate result among all of the math libraries we have tested, and thus rlibm32 has the most speed up over crlibm. So overall, our evaluation, the result of our evaluation tells us that rlibm32 not only produces correctly rounded results for all inputs, but is faster than mainstream math libraries that have been optimized for decades. And these mainstream math libraries don't produce correct float results. In conclusion, we make a case for approximating the correctly rounded results of the elementary function instead of the real value. And we use LP formulation to generate the polynomial. And to make the LP formulation feasible for 32-bit representation, we make 3 contributions. Instead of trying to generate a single polynomial, we generate piecewise polynomial. And second, we use counterexample guided polynomial generation technique that was inspired from program synthesis. And third, we propose methodology that supports various sophisticated range reductions. The resulting elementary functions that we create not only produces correct results for all inputs, but is faster than existing math libraries. Our overall goal in the rlibm project is to make correctly rounded math library to be mandatory rather than a recommendation by the standards like IEEE 754. Thank you very much. rlibm32 is available online, and we're continuing to create more correctly rounded elementary functions. So give them a try.
Thanks a lot, Jay. Great talk. I love, again, I think we have a lot of nice vision statements really clearly in this session, right? Like figure out post-Dennard scaling here. We got, make languages require correctly rounded implementations. I love that. There are a couple of questions here in the chat. I think I'll just ask them for reasons of time. Johan asks, how hard would it be to extend this approach to other number systems? So I assume everyone's thinking, posit or something like that.
So it's actually not. So there's a couple things. Our idea itself actually directly applies to other number systems. So for example, in our paper, we show and we create correctly rounded results for 32-bit posit. And I presume that our idea can be directly applicable for other number systems like log number systems and so on. The question is, this is kind of the question that I had also when I was creating the posit number system is, all of our implementation is written in double representation. We evaluate all of our polynomial in double and then produce a value in float. We also do the same thing. We evaluate the polynomial in double and then produce posit representation. One of the questions that I always had is like, does it even make sense to evaluate things in a completely different number system and produce a value in a, again, a completely different number system? But yeah, our idea definitely applies to other representations.
Absolutely. And I love this question. I remember the first time I realized that like rounding to double and then rounding to float wasn't the same thing as just rounding to float. And it's one of those like gotchas. And I assume that's what those bugs were when you were showing the two versus 3 of them. It's always kind of surprising. Another question we had is, could you say more about how the rounding intervals are computed?
Oh, sure. So there is a high level, like the high level idea is basically when you create, let's say for float, when you create a correctly rounded result for float, you basically try to identify, the range of values that all rounds this correctly rounded result. Now, if you know exactly which representation you're computing for, again, for float, and if you're using a specific rounding mode, you can actually exploit these ideas to really efficiently compute this rounding interval. So for example, let's say the correctly rounded result is V1, and then there are two values, V0 and V2, that are right next to this correctly rounded value. And if you're using, let's say, round to the nearest, you know for sure that the exact middle point between V0 and V1, right? Any value greater than that will always round to V1. And again, between V1 and V2, you take the arithmetic average, and that point, any value less than that point will round to V1, right? Again, there's, this little nuances with pi goes to even and things, but you can definitely compute exactly what the rounding interval is really efficiently.
Nice. There are some several more comments and questions in the thread here in Slack. So please check those out, and folks continue asking, and we'll keep that discussion going. But I think for now, I'll hand it back to the big boss to kick off the next talk.
All right, thanks, Zach, and great talk, Jay. The next speaker is Ignacio Laguna. Ignacio is a computer scientist at the Lawrence Livermore National Laboratory, and he's interested in a lot of stuff at the intersection of programming languages and HPC and numerical correctness. And he'll be talking about some of the tools he's built in this next talk.
Hey, thank you. Can you hear me? All right. Okay, so yeah, thank you very much for inviting me. Very excited to be here and present here. So today I wanted to share some of the work that we're doing to understand inconsistencies, numerical inconsistencies due to compiler optimizations. And this is work in collaboration with Cindy Rubio Gonzalez at UC Davis and Hui Guo, who's now at Facebook. So we have several scientific applications at the lab, right? And many of these applications have to be ported to different systems, right? So porting means that we have to run the application in a different platform. Maybe that platform uses GPUs or different compilers and libraries. And we sometimes get problems in terms of numerical reproducibility. Alison presented some of the similar problems she sees in their climate codes, right? And when we see these problems, programmers have to consider several things, right? So round-off error is, of course, the main culprit of everything, right? If you don't have round-off error, possibly we wouldn't see these inconsistencies, numerical inconsistencies. But really, the way I see it is that programmers have to look into other aspects and consider other things in the application. One of them is the precision they're using. Most of the codes are using double precision, but sometimes some kernels can use lower precision, right? So that's important. What compiler is used? Is the code using a proprietary compiler versus an open source compiler? Because they have different philosophies on how optimizations are applied into the code. Right, so the language semantics, right? So the languages we use in high performance computing typically underspecify floating point, right? So that's important. The architecture is also very important, right? The CPU is not the same as the GPU, and there could be differences in how the floating point is implemented there. And of course, optimizations, right? So in the rest of the presentation, I'm going to show you some of the studies, some of the work we're doing to understand better what happens when you have numerical reproducibility when different compilers are used and different optimizations, and how we can solve these problems. So there are two classes of comparisons, right? So we port systems and compile and run these codes in different platforms. There are two classes of result comparisons that can produce inconsistent numerical results. So one is when you compile the code and run it on the host or on a CPU, and then compile with a different compiler and run it on a GPU, and then compare the results. If we have a difference in the results, this is what we call host to device variation. And the other case is when we run everything on the CPU, not GPU, everything on the CPU, but we use different compilers or maybe different optimizations between two runs or different executions of the application, right? So that's the other case that is important. And so here's an example of a real case that happened a few years ago at the lab. So this was from a small application, hydrodynamics application that was ported into a new system. The new system was IBM Power 8 using NVIDIA GPUs. And so this application computed an energy value. And what happened was that with a particular compiler and optimization level, we were getting a very different energy value, as you can see here in the slide. And you would expect to see small differences when you use a different compiler or when you use fast math or different optimization levels. But this case was, the difference was really, really large. So it was significant. And so programmers wanted to debug this case, and it took a lot of effort to debug it, several weeks of effort. And so this shows that we actually need tools to automatically or to help the programmer identify where the problem is coming in a large code. When they see these cases, right? So 2 research questions we are interested in answering. One of them is how can we systematically identify programs that produce such variations? So this is one example, right, from an application. Alison probably has other examples as well. But we want to generate more cases like this because we want to understand what is the pattern that these codes have that produce these inconsistencies. So we want to be able to automatically generate many test cases like that. And I'm going to show you a tool called Variability that allows us to answer that. And the second question is, can we design tools to isolate the line of code that induce those variations, right? Because you can imagine a large application, it's difficult for a programmer to know where the problem is coming from. And I'm going to show you a tool called pliner that helps us to answer that question as well. So Variability is the first approach I wanted to share. So Variability is a framework to quantify floating point variations in heterogeneous systems. And so the way it works is that basically we use differential testing and random program generation. So we randomly generate many tests using a subset of C, of the C grammar. And then we compile and run those tests on different platforms and different compiler optimizations and do a search for cases where we see variations or numerical inconsistencies, right? And then we report that to users, and that helps us understand what are the, given a new system with, let's say, 5 compilers, what is the compiler that would tend to produce more consistent numerical results, and that helps programmers in choosing a compiler in the system. And also helps to develop tools as well, because we really need to have many of these cases. So I'm going to show you some of the tests that we have found that are interesting. So this example is fairly simple, simple test that is automatically generated. You don't have to understand the test because it's a random test. But we can you can see here the output here is slightly different. Here we run on the host on a CPU using the XLC compiler, and the other version is run on the GPU. So as you can see, the difference is not large, which is what you would expect. But this second example here, a larger test, shows a significant difference when you run on the CPU and then on the GPU. So one is an AND using the client compiler, and the other one is a number using the MVCC and running on the GPU, right? Another example is when we use, we found these cases where we use actually O0, which means we're telling the compiler we don't want any optimization at all, right? So you say, hey, I don't want you to optimize the code, you use -O0, but still you can see variations and differences. And this is the case for these 2 examples when we run these both of them in the CPU architecture using the XLC and GCC compilers. So you can see that the results are very different, right? So we can generate cases like this, which is very useful in developing tools. It was actually very useful in developing pliner, which is the other tool that I want you to that I wanted to share today. So pliner performs a search in the program and identifies the lines of code that could induce these numerical inconsistencies due to compiler optimizations. And so this is a quick overview. I don't have the time to go into details in the technique, but just very quick overview. So we start with the source code of the program, and then we perform a hierarchical isolation of code regions. And in each code region, we increase the precision and then compile and run to see if that actually solved the problem, right? So increasing the precision tends to solve many of these optimization problems. And then we report that to the user, and the user can go and see, okay, so in these lines of code, this is where the problem is coming. They could transform the code, or they could increase the precision there, or they could do a number of things. Again, I invite you to look at the paper for more details. Here's a diagram of how we split the code in a hierarchical manner. We start with a function, then with loops, inner loops, basic blocks, and lines. We use a smart search algorithm, like a delta debugging algorithm, and at different levels increase the precision to see if that helps in solving the problem. And we have evaluated it as well with the example that I presented before of the mini application, and with also 50 cases that were generated using Variability. And it's fairly accurate in identifying the line of code that is the origin of the problem. So 41 out of 50 cases correctly identify for the XLC compiler, and 46 out of 50 for the GCC running in Intel compiler. And with this, in summary, as you know, many factors affect floating point results, right? So compilers, hardware optimizations, precision. Parallelism is another important aspect that I didn't mention, and I would like to see more talks talking about that, because parallelism is another thing that can actually affect the results, right? So if you receive messages in different orders, right, from different runs, that could also produce different numerical results for these large parallel applications. And so the really takeaway the key takeaway that we found is that programmers of this application must be aware of the default behavior of compiler optimizations, because they tend to do things that, if you don't know what they're doing, it could really change what you're expecting. And I presented two tools here: Variability, that generates programs automatically that produce these numerical variations, and pliner, that identifies code lines that induce these numerical inconsistencies due to optimizations. And with this, that's all I wanted to share. I'll be happy to take any questions.
Great talk. And I think more tools like this are super exciting. There are several questions here in the Slack, but I think once again, I'm going to invoke moderator privilege. With pliner, one thing I'm curious about, this approach, it seems like it's a very different approach, but there's some similarity with tools like Santosh's et al.'s Posit Debug, or some of the earlier work we've done on HerbGrind, where you have like a shadow execution in higher precision, and then you look to see when there's a discrepancy. Whereas here, it's I guess like more delta debugging approach, and you're locally increasing, like you have a problem and you're sort of locally increasing precision to see if it goes away. I was wondering, like between those two approaches, what maybe some trade-offs are, or if you considered using other techniques or combining them in some way.
Yeah, no, I think those, I mean, in a general sense, we're doing something similar. The one difference is that we wanted to apply this to an actual application, right, running on C, C++, and we wanted to make sure that we could do this in a C, C++, possibly Fortran program, possibly running in parallel. And, in a sense, this was kind of like the approach that we had to use. But in general, I would say yes. I mean, we found that increasing precision many times helps to solve these problems, because the compiler optimizations that cause the problems usually assume that you use normal numbers all the time. But the moment you have like subnormals and things like that, then that causes problem, right? And then when you increase the precision, yes, you're gonna be able to find what the problem is.
Pavel also had a question about future proofing. Maybe is there a way that we can write our code to be more robust to different compiler changes or library changes in the future? Pavel, I don't know if you want to expand on that, or.
Yeah, I mean, I think that's a good description of the question. Yeah, like, you're talking about GPUs where you can run on the GPU and find the problem. But what if, is there something you could do to like search for problems that might occur?
Do you mean searching in the GPU? Sorry, I don't think I understand the question.
Well, there's like this traditional approach where you use something like randomized rounding, right? And you hope that that tells you which parts of the code are like especially sensitive.
Oh, I see. You mean
the way
like
things are rounded.
identifying.
Yeah.
Right. So we want to identify cases where the compiler optimization actually, induce the problem. I'm not sure if randomizing would actually fit in this model, where the compiler change the code, right? And then you get a different result. I think those approaches are helpful for other problems, not necessarily this one, right? Maybe identifying sensitivity in the code and things like that. But I'm not sure if I would say sensitivity to compiler optimization. That's the part I'm not sure, right? Yeah.
Yeah, that's very interesting. Yeah, good point.
And I think that does bring us to the end of the time, but definitely a lot of good discussion queued up in the thread of the talk. Thank you so much, Ignacio. It was a real pleasure to see you here at FPTalks. But I think we'll hand it back to Pavel for our next speaker.
Yeah, and I've got to say, I think every single speaker, we have had more questions than we could in the Slack than we could handle in person. So, I think just a great opportunity to sort of continue discussion and make sure to sort of go back and answer those. Okay, so our next speaker is Rocco, and I see he's just joined actually from inside my office. Rocco's a PhD student at the University of Utah. He works with Zvonimir Rakomarek, and he's been working on numerical analysis and numerical error basically since the start of his PhD, which is a couple of years now. So Rocco, please take it away.
Thank you, Pavel. Let me share my screen. Okay. Hi, everyone. My name is Rocco, and I'll be talking to you about our recent work on rigorous round-off error analysis for probabilistic floating point computations. So the goal of worst case round-off error analysis is to bound the error between an ideal expression, f of x, and the floating point counterpart, f cap of x. The resulting error bound is rigorous, meaning it holds for any x in the input range AB. So now let's apply worst case analysis to a real world application for GPS sensors. So GPS sensors provide latitude and longitude coordinates that are naturally noisy. This imprecision led to the suggestion that coordinates from a GPS sensor should be corrected by adding a probabilistic error term, so to shift the observed coordinates into an area of high probability for the true coordinates. And our goal is to bound the round-off error stemming from the double precision implementation of the correction. So here we report the correction for the latitude coordinate. The one for the longitude is very similar, so we can focus on the latitude correction only. The correction term consists of the variable radius, which is Rayleigh distributed, the variable angle, which is uniformly distributed in the interval 0 to pi, and a constant value. We ran worst case analysis on the correction, and we get an error bound that is in the order of 10 to the 286. So this value is close to the max representable double in floating point, and is somehow of little use from an implementation perspective. The reason behind such an enormous error is that in worst case formulation, the worst case formulation, sorry, ignores how the input variables are distributed. And so regions of high probability that we can call typicals are treated like regions with minimal probability mass, the outliers. So to tackle this limitation, we need a probabilistic analysis. And in our work, we show how to derive the distribution for f of x and for the counterpart in floating point f cap of x directly from the input distributions. Then we can use this probabilistic analysis to maximize the error conditioned on the computations landing in the typicals. To do so, we need somehow to adapt the standard model of floating point arithmetic to deal with random variables. So all we know is x has a certain distribution that we call dist. For example, a Rayleigh distribution in our GPS example. But there are some other things missing here in the standard model. First, how to derive the error distribution E. And in our work, we show how to build the error distribution directly from the input variables. And also how to compute operations between random variables. While this is standard when the inputs are independent, what is normally called convolution, like x plus y. But this is a much harder problem when the inputs are dependent. So if we go back to our GPS case study, now, because we are dealing with random variables, we can set a confidence interval like to 99.9999% and compute the round-off errors for the typical computations. So we ignore the very rare outliers. With this setting, we get an error bound that is in the order of 10 to the minus 15. So close to machine epsilon. To summarize, using our probabilistic analysis with a confidence interval set to 99.999%, the round-off error of the GPS correction is bounded by 10 to the negative 15. On the other hand, the worst case error, which has an implicit 100% confidence interval because it's worst case, the error is then 10 to the 286, in the order of 10 to the 286. So this shows how pessimistic worst case error bounds can be, and also how we can leverage our probabilistic analysis to compute average round-off error bounds. And this is my last slide. Thank you.
Okay, great. Thank you, Rocco. So there's a couple of questions already in the Slack thread, but I'll ask one of my own just to pop in and as running this thing. So I was wondering, how about using this to abstract over library function implementations, right? Jay was just talking about how difficult it is to build something that's half alp in every single case, but like it's a lot easier to build something that's within half an alp in 99.99% of cases, right? Can you abstract over thinking of the library as sort of probabilistic? Is there am I kind of matching up the probabilities incorrectly, or could you do something like that?
Yeah, I mean, the main limitation is, in my opinion, you need exact input distributions. So this is clearly the limitation. But when you do have known input distribution, you need to leverage this information, which is actually completely discarded when we use worst case analysis. The input distribution, even in case you have it, is completely discarded. So there is a great improvement. So you can definitely reduce the error bound, but you do need to know the exact input distribution. So if this is the case, you leverage this information.
So then how big an assumption is the choice of input distribution, right? I mean, for GPS, you know it maybe, but like, how confident do you have to be that that's exactly the distribution?
Is huge assumption, I think. I think is huge assumption. And in particular, in the GPS reading, the user might be okay with a small error, meaning the user might be okay that sometimes the error bound might get violated. Clearly, in a safety critical application, a user might not be okay with that.
And you can also even imagine filtering. Maybe you can detect these higher out, but they're going to be outliers probably in the values anyway. So you could do some kind of a filter just to toss out outlier outputs. There are a couple other questions here in the sec. Laura asked about PSI. Laura, I don't know if you want to ask that question live or. Oh, okay. Sounds like people got to be muted. Perfect, perfect. So the question is, what about tools like PSI? Did you try using those to infer the distribution for the expression?
No, I didn't have. We didn't try to use this kind of tools to infer input distributions. We applied this approach to, like Pharr said, to approach where the distribution is somehow, in theory, is well known what is the input distribution and is somehow exact, which is certainly something, a corner case, we can say, is a very specific situation where you know the exact distribution, but we never try to estimate the input distribution, because I don't know how it can affect our rigorousness.
So maybe a follow-up question kind of on this vision. I really like this idea of taking the input distribution into account. I suspect that's one of the places where we can also recover some of the performance, Matt was talking about at the beginning of the session, and some of the stuff Theo was looking at in the previous session. I wonder how far we can push this idea. So have you considered, tuning, this sort of performance accuracy trade-off also based on input distribution? Like, I want the fastest, most accurate version of the code for most inputs most of the time. We keep weakening the spec, but presumably we can keep getting more and more performance. Do you have any intuition about that?
Yes, I agree. Given the strong assumptions we need to use this sort of analysis, now it would be very nice to work on future works like that. And similarly to what Laura presented earlier in terms of control flow analysis and the instabilities, now with this setup, it would be very nice to estimate something like what is the probability of these instabilities happening.
Absolutely. Okay, well, there are a couple other questions left in the Slack, and if anybody has more thoughts, please don't hesitate to add more. I think Rocco's in the Slack, so he'll be there. But I think with that, we're going to wrap up this session. So I'll hand it back to Pavel to tell us about the break and the upcoming session.
Yeah, so we're going to have a half-hour break. We'll be back at, I think it's 3:30 Pacific time. So as with the previous break, so I'll be sticking around here in the Zoom, but please get something, get something to eat, get something to drink, stretch your legs, and I'll see you all back here. The next session is going to start off with Peter Lindstrom's talks on compressed floating point arrays, which I think is going to be super exciting. So I hope to see you all in a half hour. And Rocco, you can share. Yeah.